We'll start our slides from the current slide. And before we get into that, let me make these few announcements. There are a bunch of them, but I'll try to move through it as quickly as possible. First question, are any of you graduating this term? No. Okay, if you know of anyone who is, it's awfully late now. There's 2 scholarship opportunities, one at UAB and one at University of Alabama, Tuscaloosa, presidential scholarships, but the applications are due by tomorrow. Okay, so if you know of anyone who is, they've got to get those in by tomorrow, 5 o'clock, I think it is. Now, this is something similar, not similar, it's not a scholarship, it's an internship. It's called the 2018 Talent Development and Innovation in Sciences Summer Internship, and it's the application has been extended until Friday, this week. So if you're interested in this one has to be due in by Friday. Now this Talent Development and Innovation in Sciences, TDIS, okay, that's what it's going to stand for. I'm not going to say all that mouthful again. But this is from the QEM, which is the Quality Education for Minorities. They've extended the deadline for this summer scholarship program to be March 2nd. The TDIS, sorry about that, summer internship program is a 10-week paid, they pay you to go to it, internship, includes housing. You don't have to provide housing for yourself, including the housing, in the Washington, D.C. area. It's conducting research projects for the National Science Foundation. So it's really a nice deal. QEM TDIS interns will also be engaged in a variety of professional development activities and can receive additional support, meaning money, okay, or they'll pay for you to do things, from QEM to attend conferences, workshops, and trainings throughout the following academic year. So it doesn't just end this summer, it continues next year as well. Please encourage your students, they're telling us to apply at and there's a website here you can go to. If you have questions, comments, concerns, you can contact this person directly. And this also includes tribal colleges and universities, that would be, Native American, but also they're really big on HBCUs as well. That has been extended till Friday, but you need to move on it. They have a couple of testimonials here from students who did it last year. So if you're interested in that, you can get it, get the website and all that. Let's see. You probably didn't receive this. Some of these you got on your email. That one, I doubt if you did. Now this one I don't know very much about, and it's a little confusing to me, but I'll tell you what it is. First Call Quality is a company, First Call Quality Services, based out of Indianapolis, Indiana. There's a phone number here. The One Stop Career Center, which is just behind us here on the other side of the building in the Millsap building, is taking applications for the job fair, which is usually held at I believe at the Bessemer Civic Center right next door to us here. And they're looking for quality inspectors, $11 an hour, team leaders, $13.50 an hour. And when? Tuesday, March 6th. That's next Tuesday. Where? At the One Stop Career Center behind us here. The time is from 9 to 1, and benefits are available. So now that I'm thinking about this, I think I have a better idea of what this is. This company is coming to the Millsap Center next Tuesday, and they're going to be interviewing people for things. So get your resume, your whatever ready to go. Okay. Applicants must have a clear background check, driver's license, either a high school diploma or GED, And automotive manufacturing experience is preferred but not absolutely required. So if you've got more questions, Ms. Brenda Thomas works at the Career Center, and Ms. Dorothy Henry. It may be Dr. Dorothy Henry. I know there's a Dr. Henry somewhere around here, and I don't know if that's her or not. Anyway, they both have phone numbers in the middle shop. So they're here, and that's what I guess it is. They're here to interview for quality inspectors and team leaders. All right, our math team still meets every Friday at noon on the Birmingham West Campus, C100. Not this Friday, though. We have professional meetings in Jasper, Alabama, so Mr. Rossi won't be here. This Friday, okay? But they also meet every Monday afternoon at 3, same place, okay? So, I think I've announced to you before the tutoring opportunities available to receive or to give tutoring. And y'all would be great candidates to do the tutoring because y'all are in upper level math courses. I know they're looking for folks. Now, this has nothing to do with you, but it does have to do with my office hours. Okay? Tomorrow, Wednesday, February 28th, 2 to 4 o'clock, we have a meeting right over there in the Ethel Hall Auditorium. Now, I have a class, 2 to 3:15. So I'm going to teach my class first, then go over there. So normally after class at 3:15, I'm back in my office. Not tomorrow. I won't be there until sometime after 4, whenever that meeting is scheduled. So just letting you know that's going to be tomorrow. Office hours won't start until sometime after 4 in the afternoon. I have one in the morning still. That's no sweat. 7:45 to 9:30 and 11:15 to 2. Those office hours are still good. It's just the afternoon won't start until after 4. Now, they're meeting us to death right now because Thursday we have a meeting from 2 to 5. But fortunately, it's next door too at the Ethel Hall Auditorium then. But I've requested that I be able to leave that one a little early because I have those meetings up in Jasper on Friday also, and because I'm speaking at that meeting, they've invited the speakers up Thursday night. I need to be there by 6. If I'm in that meeting till 5, no way I'm going to get to Jasper by 6 during rush hour. Okay? So I'm going to need to leave early. But if I can't, then I'm not going to receive the invitation. I won't be going there. So, basically from 2 o'clock, I won't be available. I'll be in my office till probably 1:45 till 2. And then after that, I'll be there and then heading to Jasper. So. And then Friday, I won't be on either campus because I'll be up in Jasper. Okay. Now, none of you are graduating, but if you know anyone graduating, next week there are meetings for graduates for this spring. Monday at 6 o'clock on the Birmingham West Campus. Tuesday here on this campus, Ethel Hall Auditorium at 1:30. Wednesday, 1:30 on the Birmingham West Campus. Okay. So if you want to get information for those folks, here it is. All right. I think that's all the announcements. It sure was enough of them. Any questions on what's going on or any questions on TRIC? Either one. Okay. I should have turned on the projector earlier. We're in section 4.7 on page 319. We just got started on this last time, and we're ready for example 2. Finally, it shows up. Okay. Graphing the arc sine or the inverse sine function. Okay. Sketch a graph of this function. Okay. So I'm going to get my pen activated properly. Any questions before we get started? What's that? Okay. Now, for the inverse sine function, your horizontal axes are numbers, of course. All axes are numbers. But they just represent numbers, okay? Your vertical axis represents, and I like to think of them this way. I know the books like to say they're just real numbers, and they are, but that is radians. Remember, with the sine function, your horizontal axis is your angle measurement in radians, usually, and your vertical axis is the numbers. This time, the horizontal axis are the pure numbers, and the vertical axis are also numbers, but they are your radian measures. Now, what will those ranges be? Horizontal axis will go from what to what? For the inverse sine. Remember the second? Okay. Okay. Remember your sine function, you know how it looks like, is not a one-to-one function, right? So you have to restrict an interval where it is one-to-one. Now we're talking sine, not inverse sine now. Where is the sine one-to-one? Okay. Cosine will be 0 to pi. Sine is minus pi halves to pi halves. Now that's the angle measure. What would be the range of your sine function? Always. Negative 1 to 1. So since we're doing arc sine now, or inverse sine, what will the domain be? Negative 1 to 1. Very good. So we'll start here at negative 1. Maybe I should make it a little bigger, don't you think? We got plenty of room. Okay. So we'll make this, well, let's start. What will your range be? Negative pi halves. I can't write. 2 pi halves. Okay? And your horizontal axis will then be something like minus 1 to 1. Okay? I probably don't have those quite even. Let me move this over a little bit. And the scaling is probably pretty bad too. But no, I didn't move it much, did I? Okay, let's try that again. That looks a little better. Okay. Now, and I'll tell you, I don't think in terms of arc sines or inverse sines, I think in terms of sines. So what I'm going to do to plot this is imagine this being my input, and that's my output, is like I'm going to plot the sine function, but plot it on this side. So, what is sine of negative pi halves? Okay, what's sine of 0? 0, okay. All right, so there it would be. Now, if it's helpful, and maybe it will be, let me go on and do this. I don't know. I don't recommend that you do this every time because it's just a lot of extra work. Give me a color. Second? Green. Okay, green, green, it's green, they say. Okay. I'm going to put my negative pi halves here and positive pi halves here and 1 here and minus 1 there. Now this isn't to scale or anything, but forget it. Let's plot the sine function. There's 0, 0, and that's why it still plots as 0, 0. Okay? How would you plot the sine function? It goes up to 1 at pi halves and down to minus 1 at minus pi halves, right? Whoops, whoop, 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 whoop. I was looking at the wrong place. Right there. Okay. May have gotten that one a little high too. Okay. All right, right about there. So basically the sine function does like this. Something like that, right? Okay. I don't know if that's helpful to you in plotting the inverse sine. But again, doing this way, minus pi halves gives you -1, 0 gives you 0, and plus pi halves gives you +1. Again, I like to think in terms of sine, but this time the curvature is backwards. Where this is approaching a horizontal slope, this approaches a vertical slope. So that's what your inverse function looks like, right? Something like that. Okay. Now, remember inverse functions? This time I'm not asking you for a color because I'm using the color. It's at 1, 1, 0, 0, -1, -1. There is your identity function, and these have to reflect across. Now, mine don't quite look like they do, because I don't draw a very good identity function. But sure enough, that's it. So here is what they were asking for in the dark blue. Okay? That's your arcsine function. I superimposed it on the sine and the identity function, just so you get the idea of the output going from. Okay? Now, I can't extend these anything past that. That went over a little bit, because then it starts curving back in. That's not one-to-one. You have to stop at that point. Okay? Good deal. Does that help? To me, that's easier to do it that way. Okay? Think of the slopes and things like this. Now, this example, too, in addition to being on the graph here, on the PowerPoint, it says see LarsonPrecalculus.com for an interactive version of that type of example. So you can go back and see, and they may do the same thing I do. I haven't looked at it. All right, to delete this, and let's see how they did it. Okay. So we'll erase that ink. And by definition, the equations y is equal to arcsine x and sine y is equal to x, that's sort of what I was doing, are equivalent on the interval. Minus pi halves the pi's for your y's, and -1 to 1 for your x's. Okay? So their graphs are the same. Yeah. As long as you don't exchange the x and the y, they're the same. So from the interval from minus pi halves to pi halves, and it starts plugging in values, which would be fine, except they're just hard to find on the graph, But you can do it, In fact, that's kind of what I did when I did the sine function, is I knew where those values were, I knew how it looked, and all that kind of stuff. But you notice they did the same thing I was doing. Pick a y, not an x. Usually you pick an x, pick a y, and then plug in what that is. Negative pi halves is -1, 0 is 0, and pi halves is 1. Those are the only three I picked. You can go back and do the others. Now, this one I find hard to plot. So I would just probably only do minus pi 6 and -1/2, and pi 6 and 1/2, because those are a little bit easier to plot there. So let's go back and plot those two here. Oh, I've already erased it. Sorry, I forgot. We won't go back and plot it. Okay. But if we had those, you do a third of the way between 0 and pi halves, that's pi 6, and a third of the way between 0 and negative pi halves, that would be negative pi 6. And then you do 1/2 down and 1/2 up. Okay. Then plot the points and connect them with a smooth curve. This is how it looked. Okay? Now, how I like to remember this, there was about a third of the way down here is your minus pi 6, and that's going to be halfway here, which is minus pi halves. About a third of the way up here, between 0 and pi halves, is pi 6, and halfway between here is pi halves. This gives you that almost linear section there that follows the one-to-one. I mean, almost exactly. And that gives you that part, and then you curve up here. I thought there was someone coming in, it was just the window shaking. All right. I usually don't do that many points because to me, square root of 2 over 2, negative pi fourths is easy to do here. It's halfway in between here. Negative square root of 2 over 2, that's about 0.707, and that would be, I don't know where 0.7 is, so it's hard. 1/2 I can do, okay, pretty close, okay. And I know this is about a third of the way up. You could do more points if you wanted to, but okay. Any questions on that? If you have a question, do a checkpoint that's on there as well. Oh, sorry about that. Here's more of it. Okay. Note that it is the reflection across the diagonal line, y is equal to x, the identity function of your sine. And that's where I started, is picture this one and then do the other one. That would be like that. Okay. But only use that portion from minus pi halves to pi halves, which will be this way then, and minus 1 to 1 that, which will be this way here then, because that's the only portion of this that is 1. Well, that's the portion that's 1 to 1 that we use. Be sure you see that figure 452, we haven't shown that, shows the entire graph of the inverse sine function. So let's go on and show that. Oh, wait. Oh, this is figure 4.52. Why they had it out of order, I'm not sure. You have to stop it here and stop it there. But I said, yeah, let it extend over because you can't go there. No longer 1 to 1 anywhere past certain points. It includes the points, but not anything beyond that. Okay. Why? I would have shown this figure first and then done the other. They did it backwards. Okay. Now, remember that the domain of the inverse sine is the closed interval from minus 1 to 1, because that's the range of the sine. And the range of the closed interval, minus pi halves to pi halves, that's because that was the domain, the closed domain of your sine function. Okay, now we move on to other inverse trigonometric functions. What's the first one that comes to mind after we've done sine? Cosine. So let's take a look at cosine. The cosine function, remember you started off just like we did before, is first considering the cosine function. Now, all depends on what segment you use. Since most of the time, most of us like that first quadrant. Let's just start at 0 here, and you notice the cosine is decreasing in the first quadrant. So continue down before it turns up on itself. And you can't go back here because the only part that does the horizontal line test would be 0 to pi. And you can include the endpoints. Okay? So this is different from sine. Sine, since sine goes in this range, you can go negative pi halves to pi halves. Not with cosine. That would be failing the horizontal line test. So you have to go 0 to pi. Okay? Because that is a strictly decreasing function, monotonically decreasing, that is the part that we use. It's 1 to 1 on that. Consequently, on that interval, the cosine function has an inverse function, the inverse cosine function, and it's denoted by, just as we did before, y is equal to arc cosine of x or inverse cosine of x. Remember, this does not mean 1 over. that's dealing with a function, f inverse or whatever, that always means inverse function, not 1 over. Okay. So. Similarly, you can define the inverse tangent function. So we're right by the cosine. That we'll come back and do that. Let me make sure. Yeah. Okay. Inverse tangent function by restricting the domain of y is equal to tan x. Now, someone tell me something about y is equal to tangent x. What are the characteristics of that function, that graph of the function? It's what? Okay, yeah. Now the inverse tangent function will be sideways. I was asking about tangent. It goes from minus infinity to plus infinity between what? Yeah, negative pi halves to pi halves. Remember, if you go back to the cosine function here, because tangent and sine over cosine, you can't divide by 0, you can't divide by 0. So it's not even defined at negative pi halves and pi halves. But between that, it goes toward negative infinity here, never touches negative pi halves. It can't. It'd be dividing by 0, so you can't do that. It goes through the origin and then goes up and never touches pi halves. So that's the tangent function. Then, like you say, flip that over and it's horizontal. Okay. So you're absolutely right. That's what the inverse tangent looks like. Okay. The difference is between it and sine. Sine included negative pi halves and pi halves. Tangent cannot. It's open and a full way. So the following list summarizes the definitions of 3 most common inverse trigonometric functions. I don't even want to consider what an inverse secant or inverse cosecant, or even inverse cotangent. That would have a little more sense. But guess what? We hardly ever use those. So we'll only stick with inverse sine or arc sine, inverse cosine or arc cosine, and inverse tangent or arc tangent. Those are the ones we usually deal with. Okay? So, since the sine of y is x, that's the y only goes, y is this way, y only goes from minus pi halves to pi halves inclusive, and the x's go from plus or minus 1 inclusive. Okay? Our cosine, the x's are still plus or minus 1, but the y's have to be from 0 to pi, inclusive there. Okay? So that changes a little bit. The arctangent, or inverse tangent function, which would be this, equivalent to this function, the x's can go from minus infinity to positive infinity. So that's where they go. Okay? The y's are restricted between minus pi halves and pi halves, not including the endpoints. For sine, they do include the endpoint. The inverse tangent cannot include the endpoint. Okay? So x's go from minus infinity to infinity. The y goes from minus pi halves to pi halves. Okay. Make sense? All right. So with that in mind, here now are the 3 inverse trigonometric functions again. The arc sine that we did earlier, okay? Whereas sine has almost horizontal slope here and here. The inverse sine has almost a vertical slope here. That's what I remember. And the slope is 1 to 1. Here it goes to 1 to 1. Okay? There's your domain and your range, just as we've described before. What was the range of the sine function minus 1 to 1 is the domain of the inverse of the arc sine function here. Well, so it's the range of the sine function where it's 1 to 1. What was the domain of sine, negative pi halves to pi halves, becomes the range of the inverse sine. Negative pi halves to pi halves. So that's how it works. Now, the inverse cosine, always I have to stop and think and struggle with it a little bit. Okay. But here's the things to remember. Because the cosine x equal y starts at 1 and goes to -1 through pi halves, it's 0 to pi halves. This now is at y is equal to pi halves and x is 0. Okay? This is x equal to pi halves and cosine is 0. And y is equal to pi halves. The inverse cosine, the x would be counted as 0. Okay? And this was 0, 1, so this has to be 1, 0. Okay? And sure it's here. Okay. We're doing the inverse trig functions. We're on bottom of page 320. Okay? Inverse sine, arc sine. Now cosine, the way I would do it is think in terms of cosine. Okay, so it starts at 0, 1, goes to pi half 0, goes, and pi negative 1. So flip all those around. 1, 0, 0, pi half, -1, pi. So whereas the cosine function was decreasing, the inverse cosine also has to be decreasing. Okay? So just a little different. The x values for your cosine are positive from 0 to pi, so your y values are positive from 0 to pi. You can't have inverse cosine be negative. Can't happen because the x values weren't negative before. Okay? So think in terms of that. Your tangent, remember the tangent function did something like that. Now the inverse tangent at minus pi half, you have a horizontal asymptote. Pi half, you have a horizontal asymptote because those places you had vertical asymptote before. And goes through 0, 0, and then goes through pi fourths, it went to 1. Minus pi fourths to -1. So those are the same key points you had before. And this extends infinitely in this direction, infinitely in x in that direction, never touching negative pi half to pi halves. The main negative infinity because all real numbers range excluding the endpoints negative pi half to pi halves. Okay. So there's how the inverse functions look. Now, think of doing these on a calculator. Okay? Your only answer, if you're doing inverse sine there, you can have a negative value or a positive value. They're going to be between pi minus pi halves and pi. So what that means, to cover the rest of the unit circle, you have to then either add or subtract some portion of it to get there. Same thing here, your arc cosine is only going to be a positive value. It could be 0 here and a 1 here for y value. I mean pi here for y values, but it can never be negative. The inverse cosine can never be negative. You can take the inverse cosine of a negative number as long as it's between -1 and 1. I mean not -1 and 0. Okay? For inverse tangent, if you're going to be stuck just like for sine between your outputs are going to be between minus pi halves and pi halves. If you had an angle somewhere outside of there, then you have to add or subtract something from it to get the periodic nature of it. Okay. All right, the example 3, top of page 321. Find the exact value of the inverse cosine of pi halves over 2. Now again, I may be backward in my thinking, but because I don't think in terms of inverse functions or arc functions, I think in terms of sines and cosines and tangents. So what I want you to do here, is tell me what you project the answer to be. Just make up a variable. Give me a variable that's going to be the answer to that. Okay? And again, I think of it this way. For a trig function, sine, cosine, tangent, you operate on an angle and gives you a number. So here you're operating on a number, and that's going to give you an angle. So to keep that in my old thick skull, I like to choose one of the Greek letters to represent that angle. Do you have a favorite? If not, you can use any letter you want, English or Greek. I don't do Cyrillic. Say again? B? Is that what you said? Okay, yeah, we can use B. Okay? Now, that's the first thing I would do. Pick the value that you're looking for, B. Don't know what it is yet. Let's rewrite this as an equivalent equation then. Dropping the arc. Okay? Hint, hint. Write an equivalent equation to that, not using an inverse or arc function. Cosine B is equal to the square root of 2 over 2. Right? That's equivalent. One undoes the other. Right? Now, what angle B has for its cosines root 2 over 2? Remember, you have to be in either the first or second quadrant. Please tell me you remember that. Well, angle B gives you a cosine of B would be root 2 over 2. Say again? If you remember your little rule, these are sines to begin with. 0 over 0 over square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. 45, which is in radians. Halfway between 0 and pi halves. Pi fourths, that's it. Pi fourths. I feel like a dentist pulling teeth. Okay, so that implies that B is equal to pi fourths. Okay, because remember the cosine, inverse cosine can only be positive, and it's going to be between 0 and pi. That's it, and that's the only it. Okay? How about this one? Arctangent equal to 0. You want to come up with a variable for that answer? Theta. Okay, here's a good old Greeky. Okay? And give me an equivalent equation to that one. Tangent theta is equal to 0. What theta would that have to be? Where is tangent equal 0? Say again? 0. Exactly. Theta would have to be 0 for that one as well. Okay? C, that's yes in Spanish. What would an equivalent, what would be your variable here? You pick a variable, any one you want to. You can use the same ones before, you can use different ones, I don't care. What variable would you like to use? Say again? D. Okay, D will work. Okay. When you get to calculus, it won't work as nicely. Okay. Give me an equivalent expression, equivalent equation to that one. The tangent of D is equal to -1. Okay? Now, where is tangent equal to -1? At what angle? Anybody? -π4 perfect. That would imply that D would have to be -π4. Okay? Because the tangent is negative infinity as it gets close to -π halves, come up to -1 at -π4, 0 here, 1 at π4, and so on. That's it. Good deal. All right. Let's see how they did it. First, the A part, because, again, you know, because the cosine of π4 is √2/2, that means, and that π4 lies between 0 and pi, it follows that the arc cosine of, basically it's saying, because this is the answer, this is the answer, okay? And to me, that's not as intuitive. I think what we did, I don't know, maybe you don't like my backward way of thinking, write down an equivalent expression. And you're saying the same thing. What angle theta is going to make the cosine of that angle equal √2/2? And you came up with π4. So they just started with that, you know. Okay? So that has to be π4. The next one, because tangent 0 is 0, 0 lies in between -π halves and pi halves, it follows the arctangent 0 is 0. Yeah. And same thing here. I just like to do it. I don't like to write down the answer and say, and that, therefore this is the answer. Okay? I mean, think through it. You know, name it an angle. Tangent B is equal to -1. What would that have to be? Well, it would have to be -π4. So we got there the same way, but it's just a little more obvious you thought through it properly. Okay? Now, by definition, the values of inverse function are always in radians. I know we like to think in terms of degrees, but always give those answers in radians. Okay? Your calculators will give them either way you want. Okay? If you put down degree mode, it'll give you in degrees. But by our definitions, they're in radians. Okay? That was example 3. There is a checkpoint after example 3. They're skipping example 4. Okay? So I think we'll use this slide here for example 4. Okay. Pull out the calculators. Use a calculator to approximate the values of each expression if possible. Okay? A here is going to be the arctangent of negative 8.45. Okay? Now, I'm getting a headache. Number one, can you take the arctangent of such a big negative number? That arctangent with that horizontal thing, yeah, it goes from negative infinity to positive infinity. Yes, you can put any number, -4,008,45. You know, that would work too. Okay? So, you got a calculator? Some calculators will say arctangent, others will say tangent to the -1. Whichever your calculator says, that's what you do. Basically just punching it in or pressing it in if you're not from the South. That would be approximately what? Say a little louder. Okay. Negative 83? That sounds like a degree to me. Okay, let's get it in radians. It's what? 1 point, what? 45. Okay, that was close enough for me. Okay, now the reason I said that, but the other was negative 83, right? Is what you said. Because that's such a large negative number, you're getting closer and closer to the negative pi halves, which is negative 90. So negative 83 made a lot of sense. And pi halves is about 1.5, right? So it's very close to negative 1.5. So yeah, those are both very reasonable numbers. Okay? The B one here. Whoa, goodness gracious, what happened to my, okay. B. All right. The inverse sine of 0.2447. What's that going to be close to? Anyone want to hazard a guess? Say again? 0.247. 0.247. Okay. Now they look pretty similar, but actually that should come as no surprise. If you think about the graph of either a sine function or an inverse sine function. Whoops, went the wrong way on that. Okay? Because guess what? This part in the middle, close to 0, is almost 1-to-1. Either way you do it. So in radian mode, not in degree, in radian mode, the sine of a very small angle is going to be very close to its value, and the inverse sine of a very small number is going to be close to the angle value. So that's not at all surprising there. Now, bigger number, not going to work, but you know, the small one's close to 0, that's going to work. In fact, I was a little surprised that 0.2447 worked that closely, because that's not all that close to 0, but it is close. So let's do C, which is yes in Spanish. And that would be arc's cosine of 2. And what would be that approximate value? Say again? Error? What did you do wrong on your calculator? It's not in the domain, because the arc cosine's domain is only between -1 and 1. Sometimes they'll say domain error, or sometimes just error. So how do they put it? An error message, okay? Because the domain is only between. So does not exist. That's what I'm going to put. Okay. And they have a checkpoint there. Definitely take a look at those. Any questions? All right. Now we're going on to compositions with inverse trigonometric functions. Okay? Now, we know that for all x's in the domain of f and f inverse, now this is general functions, any old function, inverse functions have these properties. Okay? F of f inverse of x, as long as x is in the domain of the inverse function, that's going to equal x. And f inverse of f of x. If they're inverse functions of each other, that's going to be x2, but this time that x is in the domain of f, whatever your f is. That's true for any and all functions that have inverses. It's got to be true. That's how we verify that they are inverse functions. So if we think of this, the inverse properties of the trig functions, if if x is between -1 and 1, it's like a sine or cosine function coming up, and negative pi, y is between negative pi halves and pi halves, that means it's got to be a sine function, because an inverse sine. Then the sine of an arc cosine of x is x, if x is within this range. Notice you couldn't have a -2 there, right? Because it would be outside. And the arc sine of y would have to be y, as long as the y is in those values. You can't do the sine of 3/4 pi, 3/4 pi, because that's not inside. Okay? So, somebody have to guess here. And similarly, if x is between -1 and 1, just like here, but now your y is between 0 and pi, that can't be sine, that has to be cosine, and inverse cosine. So the cosine of the inverse cosine of x is going to be x as long as x is between these two values, and the arc cosine of cosine is going to be, cosine of y is going to be y as long as y is between those two values. That won't work if y was negative pi thirds. Can't do it, because that would be outside. And if x is any real number and y is between minus pi halves and pi halves, then the tangent of an arc tangent of x is x. For any real numbers, you can get that. And the arc tangent of tan y would have to be y, but then your y's have to be between those. Okay? So, these inverse properties do not apply for arbitrary values of x and y. Can't do this one. You can do the sine of 3/2 pi. There's no sweat there. But it's not going to give you, when you take the inverse sine of that, it's not going to give you 3/2 pi, because 3/2 pi is not in the range of inverse sine. Inverse sine is between minus pi halves and pi halves. So this will give you a value between minus pi halves and pi halves. It will not give you that value. Well, what is the sine of 3/2 pi? Okay, sine starts at 0, goes to 1, at pi halves, 0 at pi, -1 at 3/2 pi. So that's going to be -1. If you take the arc sine of -1, that's going to be minus pi halves, not 3/2 pi. Not. Okay. Now, if you think on the unit circle, that's 0, pi halves, pi, 3/2 pi. That is the same as minus. But the numbers are not the same, but it's the same position. Okay. In other words, the property arc sine of sine y equal y only works when you're within the range of arc sine. Y is between that. And that is only between minus pi halves and pi halves. Because you can't take the arc sine, you can't have a value for arc sine that's outside of that. You just can't do it because of the one-to-one nature. Not valid for anything outside of it. So you cannot use that property that this one right here, this is good for all y's. It's not good for all y's. It's only good for y's that are in the range of arc sine, meaning in the domain of your one-to-one portion of sine. So that's why 3/2 pi just won't give you 3/2 pi. It gives you an answer, but it's inside the range. Okay. So example 5 here. We haven't skipped any, have we? Nope. The tangent of the arc tangent of -5. Anyone want to hazard a guess what that would be? What's that? Okay, -5. Perfectly fine, because the arctangent of you can do an arctangent of -5 because arctangent has its domain all real numbers. It's going to give you some angle between. It's going to be a negative angle between -π½ and 0. Okay, and then when you take the tangent of that, you got to wind up with -5. So yeah, that works perfectly. Okay, how about this one? The arcsine of the sine of 5π/3. Now, let me show you how I think of this. I like to see things rather than just always thinking out. Some things I like to think through, but this one I want to see. I can do this. I can take the sine of 5π/3. Okay? I think of this as π3, 2/3 pi, 3/3 pi, which is pi, 4/3 pi, 5/3 pi. Ha! Yeah, there it is. The sine of that is, and I don't know if you want to think unit circle or wherever you want to think, that's going to be some value. Okay, the sine, remember, let's do our little others here. This would be the sine of π6 would be 1/2 square root of 2/2. That's π4. This is square root of 3/2. Okay, so this one is going to be, it's the y value, so this is going to be minus the square root of 3/2. Right? All right, that's what sine of π3 is. So sine is the negative in the fourth place. Okay? It's the y value. Okay? Now, the arcsine of that number there is going to be what though? Where is arcsine defined? Between -π½ and π². So where is that in that part of the domain of the range or whatever you want to call that? This would be, what is the angle here? Well, use the reference angle. That's going to be minus π3. This angle here, that's π3, remember? This is minus π3. That's the angle there, so this answer is going to give you minus π3. I like to do it sort of graphically. Now, maybe you have a better way to do it. If you do, fine, go for it. Use it. Okay, how about that third one? The cosine of the inverse cosine of pi. What do you reckon that's going to give? And by the way, notice that this answer here is not that answer there. You know, you can't do it because this thing is outside the range of your inverse sine. So you can't have that value. Okay, how about cosine of inverse cosine of pi? Second?
You can't.
Why not?
Because it's not within the...
Yes, it's not within the domain. You cannot take, remember the only values you can take inverse cosine of are between -1 and 1. That's the only values. Pi is outside that. So this does not exist. Okay, does not exist. Okay, now that's how we did it. Let me erase my stuff so you can read what they do. Let's see. Because -5 lies within the domain of the arctangent function, the inverse property applies, and the tangent of an arctangent of a value that's within the domain is going to give you that same value. Exactly. Okay? This one, 5/3 pi, does not lie in the range of arcsine function, which is only between -π½ and pi. has, okay? But that the angle does lie in that on the unit circle type thing, so it gives you minus pi thirds, which is the same as that. So what they do is subtract 2 pi from it, give you the equivalent angle, or what do they call it, coterminal angle with that. And so that's outside, subtract 2 pi from it, and there you come right back with them. Now, if you like that better than drawing the pictures, fine. You can do that. Okay? And that does lie in the range of the arcsine function. So the arcsine of sine of pi thirds is going to be the arcsine of sine of negative pi thirds, because those have the same values. So that is in the domain, so that will be negative pi thirds. But it's not the same as pi thirds pi. Same place, but not the same value. Okay, the expression cosine of inverse cosine of pi is not defined because inverse cosine of pi is not defined, because you can only take the inverse cosine of something between minus 1 and 1. Only. Okay. Remember, the domain of the inverse cosine function is minus 1 to 1, just like for inverse sine. Whoa! Last slide that's given here. Okay? But there are 2 more examples that are not given here. So let's do example 6. How are we doing on time? Okay, good. Find the exact value of each expression. Okay? The tangent of the arctangent, arc cosine of 2/3. Only knew for tangents of arctangents, not tangents of arc cosine. So guess what you're going to have to do? Or my preference in doing, draw a picture. Now, yeah, you can pick up your calculator and see what it gives you. It'll also give you a value, okay? But let's do, and this says exact value, doesn't it? And your calculator will sometimes round off, okay? Because it can only do decimals, okay? Well, most of the time. So what I would do is I would draw me a scale here, and we want the arc cosine of 2/3, okay? Now that's going to be some angle theta, right? I'm using theta. Is that okay with you? That's some angle theta, because an arc cosine operates on a number and gives you an angle. Now, no, the books don't like to say it that way, but I like to think of it that way. So this equivalent expression would be that you write that for me. Equivalent equation to that one. Cosine of theta is equal to 2/3. Okay? So therefore what I'm going to do, and again, it's a little bizarre to do this, I'm going to not draw me a unit circle, I'm going to draw me a 3-circle. Okay? Which is not a really good name for giving anything. So there's my something like a 3-circle, right? Why did I choose a 3-circle? What is cosine of an angle? Call another hen. Cosine of an angle is adjacent over hypotenuse, right? So that's why I chose 3. That's always going to be your radius of the circle. Your hypotenuse is your radius, okay? So the adjacent is going to be 2, so we're talking about an angle somewhere about there, okay? The adjacent side is 2, and the hypotenuse is 3, right? Now, and this is your angle theta, okay? The one that we're taking the tangent of. Now, can we take the tangent of that angle? What is the tangent? Take the notes away. Opposite over adjacent. Oh, sorry, we don't know the opposite, or do we? Pythagorean theorem, okay? So the opposite side will be the square root of 9 minus 4, right? Which will be the square root of 5. Got it? So what will the tangent be? The tangent of that theta is going to be square root of 5 over 2. Got it. Okay? I like to fall back on my figures and help them work me through it. Okay? Now, that's pretty much what the book did too. Okay? All right? You okay with that? All right. Let me erase this then. My goodness, I'm getting so weak. All right. This one is the cosine of the arc sine of negative 3/5. All right. I just have a feeling I'm going to like this one even more. Again, there's no inverse formula you can go on because these are different functions. So what might you choose to do? Say again? I can't hear. Rewrite it, okay, but you need to give a name. What would you want to use? Oh, you like theta too. I've influenced you badly, haven't I? So rewrite that, and what do you get? The sine of theta is equal to minus 3/5. So guess what kind of circle I'm going to draw? A 5 circle. Okay, I've never heard of anything, but 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Ooh, that got off a little bit. Okay, let's just imagine that that's kind of a 5 circle. Okay? Now, the sine of that angle is minus 3/5. What is sine? Opposite over hypotenuse. Now, where will the minus go? Will it go with the opposite or the hypotenuse, or does it matter? Hint. Hypotenuse is always positive. Okay? So guess where the minus will go? At the opposite. And the opposite is always the y value. Right? So that's going to be a minus 3, 1, 2, 3 on the unit circle over here. So here is that angle theta. You see it? Minus 3 over 5. 5 being the hypotenuse. Okay? Now, I don't have my circle drawn too well, but now we want the cosine of that angle theta. First thing I look at and say, what quadrant is that theta in? 4th. And guess what the cosine in the 4th quadrant is? All students take calculus. All take technical college. All students take chemistry. Cosine's in the positive in the 4th quadrant. So this is going to have a positive answer. Okay? Now again, my circle is not very well done. But Pythagorean theorem is well done. Doesn't look like a right angle, but I did that for a reason. Because if this is, the opposite is 3, and the hypotenuse is 5, the opposite is actually a negative 3, what must the adjacent side be? Second? 4. You're absolutely right. That's why I drew mine like that. Because square root of 5 squared, 25 minus 3 squared minus the negative 3 squared, which would be 9, would be 16. Square root of 16 is 4. Positive 4 because that's where you are. So what's the cosine of that angle? What's cosine? What's cosine? What's cosine? Call another hand. And that would be 4 over 5. Perfect. Right? Let's see what they got. The first one I didn't think to check. It was square root of 5 over 2. That's what we got, right? And this one is 4 over 5. For effect. And that has a checkpoint too, especially since it felt like I was pulling teeth. You might want to do the checkpoints as soon as you can. All right, let's move on to, let's see if we can squeeze in example 7 before we run out of time. Write an algebraic expression that is equivalent to the expression that the sine of arc cosine of 3x anytime 0 is less than or equal to x is less than or equal to 1/3. Okay? All right. Now, why is that true? Because you know that arc cosine, the argument of arc cosine, the domain of arc cosine, has to be between -1 and 1. What they're doing here is making sure that stays positive. So they're only going to allow 0 here. And 1/3, x can't be any greater than 1/3 because it's about to be, 3 times 1/3 is 1. Anything greater than 1/3 would be something greater than 1. You can't do arc cosine. Everything's making sort of sense now. It's just requiring you to be in first quadrant. Okay. So it says write an algebraic expression that is equivalent to that expression. Well, guess how we're going to start this? What do you want to name it? Have a choice of names? Fred, Susie. No. Theta. Why not theta? I like theta. Okay. So this is saying that, rewrite that. Not that hard. You've done it before. Huh? Cosine theta is equal to 3x. Got it. Okay. Now, let's call that 3x over 1. So this time we will have a unit circle, won't we? Because x has to be less than 1/3. So yeah. So we will have a unit circle. Okay. 1, 1, 1, and 1. See if I can draw some kind of a thing there. Okay. And the cosine is 3x. And 3x is, so that's the adjacent side. So let's just call this right here. I picked out a point in between there and call it 3x. Right? Now, and this we know is 1. So to get the sine, we need that side. Right? And what is that side then? The square root of 1 minus 3x squared, which would be 9x squared. 3x in parentheses squared is 9x squared. Okay, and then what's the sine of that angle, theta? Yep, which would just be, opposite side is 1 minus 9x squared over 1. So guess what we've just done? We did what they asked for. Write an expression that is equivalent to that expression. The sign of that is that in terms of x. Okay? So this thing that we had here, this whole line here, is equal to that. There it is. All right. I think we ran over, didn't we? Oh, shucks. No extra charge there. Okay. We'll pick up next time just with B. Now, if you'll remind me next time, if you're here to remind me, not to go to 4.7. Just go on to 4.8. In fact, I'll write myself for that was, yeah, we had already done the last slide at 4.7. So I'll go to 4.8 and we'll come back and do that last B one there. Oh, some homework exercises. I knew you wanted some. Any of the odds 5 through 17, they're all at calcchat.com. 5's at CalcView. Do number 19, it's at CalcChat. Do any of the odds 21 to 35, they're all at CalcChat, but 21's at CalcView. Do 37, it's at CalcChat. Do any of the odds 39 to 43, they're all at CalcChat. 39's at CalcView. I can't talk. Do any of the odds 45 to 49, they're all three at CalcChat, but 45's at CalcView. Do any of the odds 51 to 61, they're all at CalcChat. 55's at CalcView. Do any of the odds 63 to 71, they're all at CalcChat. 65's at CalcView. Do 73, it's at CalcChat. Do either 75 or 77, they're both at CalcChat. 75's at CalcView. Do any of the odds 79 to 83, they're all three at CalcChat, but only 83's at CalcView. Do any of the odds 85 to 89, they're all at CalcChat, none of them are at CalcView. Do 91, that's at CalcChat, not at CalcView. Do any of the odds 93 to 97. Actually, yeah, I guess you can do that. They're all at CalcChat, and we'll hold off on the others until we finish up. Good deal.